this video is start from like the end where I managed to locate a problem with this unit, and it is a power switch that is very iffy, and 1 for the 10 times it's actually switched on, so I'm going to remove it. From all the dirt, I assume that I am honestly a first person to open it. The build quality of that device is so amazing that I absolutely can't accept that. If you take a look, it is a 3 amp power supply. This device is capable only for delivering a 3 amp. And just take a look at the wiring. Those wires, they are at least 2.5 millimeter. Those are extremely big wire. I never seen in my entire life so big wires for only 3.5 amp. That's like absolutely crazy. The dimension of the transformer, it is absolutely crazy. Let me show you that. So this is how the transformer looks for just 3 amp. It was built like a tank. We've got lots of different tabs, but they are most likely for a logic because the wiring is so small. I can see a relay here. Maybe this is to trigger the thermal protection. We've got some additional transformer. It is so heavy that I've got problems lifting it. Let me take a look here. This is the actual back. This is the actual back of the device. It definitely needs a cleaning, but we've got a beautiful fan, and that fan is blowing into that heatsink, and on that heatsink we've got a power transistors. That are not going to be a MOSFETs, those are going to be a regular beautiful transistors. We've got beefy electrolytic capacitors. I do not see any leakage, so I'm not going to touch them. They're most likely going to last much longer than the regular ones. We've got our diodes. Everything is nicely protected. That looks very bad, but it is like a wrap that you put on bare wire when you are having like a heating element and it's soaked in something. So don't be afraid of that. This is how it should looks like. We've got some very specialized ceramic resistor. Here I expect you can change the voltage because this is the main voltage input. So if the device is going to be using different voltages, here you can make changes. Here we've got a device for triggering overheating. Now you've got the device in a package that you just stick into the heatsink, but back then they put a extremely big device. Most likely it was intended for like a heater or something completely else, because it is such a massive device, such a overkill, and the wires are extremely tiny, so it's just sending a logic that looks like from a iron. I'm going to spray those rotary switches to make sure that they are working nicely. Looks like controls are being run just by a regular bulbs that are screwed in. So if we've got any problem, that can be a neon bulb or just a regular one. Let me undo it and we can take a look. That looks like a regular bulb, so absolutely no LEDs. I love that design. That is extremely nice. Here we can see we've got some trimming pot for making adjustment, but I do not have any documentation, so absolutely no way I'm going to touch any of those things. Those looks like a custom resistors for making them in parallel, so if there will be any imbalance it should go into those elements. But the build is amazing. It is absolutely amazing. Let's take a look at the side that we've got a problem, and this is our switch that is actually faulty. You can see that it is working in a kind of weird way. So let me try and do it, and let's take a look. So this is going to be extremely easy task. We have to make a measurement because some of them are switching those two poles together. For you that was 1 second, but for me it was over a month. Because it is a historical piece, I've decided to get exactly 1-to-1 replacement, and I spent crazy amount of time getting it, and I ordered couple of them. As you can see, they were never soldered, they are new old stock, and I've got 1-to-1 match. Because I was unable to wait a whole month without trying to power it on, I short circuit the wires bypassing a switch, and it started working, but the current regulation didn't work, and I'm going to tell you where the problem lies, and that was absolutely the least element that I would expect. I started from cleaning parts that are related to adjusting current, the shunts, but that was not a problem, and it was a funny problem, so I'm going to show you that in a second. But first let's mount a new replacement switch. The orientation of the switch I would like to have exactly the same as it was, so in the up position it should be short, and this is going to be that pair. So let's do it. We've got a absolutely beautiful brand new switch. And it's done. We've got it absolutely beautiful. Like in that meme, they are not going to know that we make a change. So let's try to plug it in. We are plugged into the AC. I flip the switch. We've got the bulb on and the device is working properly. Turn it off, turn it on. We've got our power switch replaced, and now I can tell you what was the problem that I need to fix. I was able to adjust the voltage without any problem, and when measure on the terminals, I've got exactly the voltage that I wanted, but the current regulation wasn't working. I was unable to set like a 3 amp output. The limit wasn't working, and it was delivering a extremely tiny amount of current that was unable to even lit up the bulb. We've got multiple things that are related to the current. We've got output for the external emitter, so this is a shunt that is joining those two terminals, and we can hook up here a external emitter if we would like to have something more accurate. This is a first point of failure. We've got our adjustment, so that was the place where I go first. On bottom part we've got lot of binding posts. The most common one is the earth terminal, and it's connected to the wiring earth on the plug. Right now in that configuration where it's not attached to anything. Then we've got a free floating power supply. Between those two pins we are going to get a voltage, and it's like a battery not related to anything, but we can tie it to the ground, and then our power supply is going to be referenced to the ground, so they are going to have the common potential into the positive, or I believe maybe we can do that otherwise. Then we've got a voltage pins and the amp pins, and they are tied together. That means the power supply is going to regulate the voltage and the current, but we can use only a current source, and that means the voltage is going to be not used, and we can go into 3 amp and, for example, charge the battery, and we do not pay attention to the voltage. It will self-regulate to give us always the selected current limit. Our use case is that we are going to have them tied together, and the power supply is going to be regulating both voltage and the current, and it will push as many amp until the limit is going to be hit to regulate the correct voltage. So that part wasn't working, and the problem was in that relay that is located over here, and it's being used for a thermal protection. I cleaned those contacts with a sandpaper, and now it's working absolutely fine, and I can get a full current. If you ever need to engage those type of relay, you can push on that element and it will tie itself, it will pull itself, and right now we've got enable a thermal protection. So that relay was related to our thermal protecting circuitry. Absolutely, completely far away from regulating a current. Let me put the enclosure and we will be able to do some basic test. I put the enclosure and we are ready to do some basic testing. On top we've got my trusty Voltcraft bench top voltmeter. We've got a 12 volt halogen lamp that is being connected to those alligator clips, and we are ended in those banana plugs. We can take a look at the power supply. Here we've got the power indicator and the thermal overload. Those are regular bulb, which is absolutely amazing. We've got a main power switch. We've got the analog emitter with ability to adjust the zero. If the needle is not pointing at zero, we can make a alignment. Here we've got ability to adjust current from 0.3 amp, 1 amp up to 3 amp. Over here we've got two BNC connector with a shunt in between of them, which is going to be external emitter. We can grab a multimeter like this, like our Voltcraft. We can go into amp mode and we can hook it up here and got a digital readout. That whole section is being dedicated for adjusting the output voltage. We've got that beautiful rotary switch that have a increment of 100 millivolts, and it go into total of 1 volt. Then we've got those switches that can add a 1 volt, 2 volt, 4 volt, 8 volt, 16 volt, 8 volts and 2 volts, and we've got a 10 volt. So that looks absolutely like a binary, like something that would be read by a microcontroller, but it's not. It's totally analog, and it's switching a high precision resistors to get a corresponding response, and we are going to see how accurate it is. I've got my halogen lamp, and we are going to connect the positive to the positive, negative to the negative, and we are going to grab a 12 volts. Let's try the external ammeter port. Right now we are in the 3 amp range, and we are reading a half scale. The full scale is a 3 amp, so we should get around 1.5 amp. I'm going to disconnect the power and remove shunt that go between those two, and now I can connect my multimeter on the amp range with the amp socket. We've got the positive, the negative, so we go with our probe like that, and I'm going to turn the power on, and we are reading exactly like we expected, 1.67 amp. I would say that this is pretty close to the center. Now let's take a look how beautiful that digital style control works. Let's pretend that I would like to replicate a battery that's got 1.2 volt. Then I'm going to add 1 volt and 200 millivolts. And what are we reading? We're reading exactly spot on 1.2 volt. A regular battery, let's go with a 1.5 volt. We go 1.5 volt, and we've got exactly spot on. Something commonly used, a 9 volt battery. I grab 8 volt plus 1 volt, and we are around 9 volt. Absolutely beautiful. Let's do a 10 volt, pretty common. 8 volt plus 2 volt, we've got a 10 volts. Let's do another pretty common voltage, a 15 volts. We go like this, and we've got exactly 15 volts. 16 volts is on that switch, and if we go all of them, we go into a 32 volts. So as you can see, that looks absolutely beautiful. If we put that device into a newer enclosure, you could easily pass that this is a digitally controlled, and the MCU is just reading binary values from a front panel, but they are using a real high quality resistors that are so precise that after so many years, if we go into a 4 volt, we've got exactly 4 volt. 5 volt for digital logic, absolutely no problem. We would like to get a 5.2 volt. This is, in my personal opinion, absolutely beautiful way of adjusting voltage, and with such high precision you really do not miss out not having a voltage meter, because as you can see, there is no voltage meter that is reading out. But with such precision, let's pretend that we would like to have a 5.5 volt. With so precision, you really do not need a voltmeter. That cheap China is absolutely terrible. I've got problem. The pot are starting having problems, and keeping a voltage is terrible. You have to be really fiddling around to get a proper voltage. But here, that is absolutely acting as a digital one. I've got 9 volt, I've got a 9 volt, so yeah, absolutely amazing. Thank you very much for watching. I hope you find it interesting. See you next time and bye bye.